Now we have 2 talks left on this track, and now with me on the stage is Boris, and we will have a talk about a North Korean malware campaign. So please give a warm round of applause, and yeah, have fun with the talk.
Hello, everyone. Great pleasure to be here. My name is Boris Larin. I'm a principal security researcher at the Global Research and Analysis team at Kaspersky. And today I want to tell you a very interesting story how cryptocurrencies, online multiplayer games, Google Chrome, zero-day exploits, and Lazarus Group can be all mixed together in a single attack. So I work in the great team, and at work, me and my colleagues, we trace the activity of APT actors, we find and analyze targeted attacks. In my opinion, Lazarus Group is one of the most interesting APT actors out there. It's a very multifaceted APT actor, which is active since at least 2009. And they perform operations of cyber espionage, cyber sabotage, and also what is very unusual for APT actors, they perform financially motivated attacks. So they attack banks, ATMs, and the cryptocurrencies industry. And they are known by very many names. It kind of gets complicated because Lazarus, it's not like one group. They consist of multiple subgroups. We know for sure that there is a subgroup that performs cyber espionage operations. And also, there is a group that performs financially motivated attacks. We call it Binorov. But of course, the most famous name for this actor, Lazarus Group, came up with the report Operation Blockbuster. Operation Blockbuster, it was a research led by Naveta, conducted by Kaspersky and other companies. It was an investigation of movie company Sony Pictures Entertainment hack that took place in 2014, right before the release of the movie Interview. Like you can see the poster for this movie on this slide. And back then, hackers attacked this company. They stole the files from the computers of employees. They stole emails. They stole this unreleased movie. And leaked all this data online and also removed all the data from the computers of employees. And we investigated this attack. We analyzed malware that was used in this attack. And we found code similarities that allowed us to attribute this attack to some other attacks that we've seen before. This was attacks on different businesses, banks, and military contractors in South Korea. And previously, actually, it was believed that these cases are not related, but these newly discovered code artifacts allowed us to attribute them to a single actor, Lazarus Group. And also, the malware that was used in this attack, it shares common code with a backdoor that we call manuscript. And manuscript, it's like signature malware of the Lazarus Group. It was used since at least from 2013. It's been actively used up to this date. And it's been used in so many attacks, and all these attacks were so noisy that we even wrote 50+ reports about unique campaigns in which this malware was used in industries that you can see on this slide and many more other industries. And the story that I want to talk about with you today, it all started when we discovered a new infection of manuscript. But it was a really interesting one because this time it was not an attack on some government entity or diplomatic entity or like military contractor, like usual targets for the Lazarus Group. It was like the victim, it was just some regular home user. The regular home user that used like our consumer version of the product. So, and this case was kind of interesting, like what would Lazarus would need from some regular home user? So we decided to investigate this case more closely, and we found out that like right before the manuscript was detected, there was also detected exploitation of Google Chrome web browser that happened like moments before the Lazarus was also detected. So the time delta between these two detections was so little, so it was sure, like we were sure that these cases are related. And this exploitation, it happened when the user was visiting this website that you can see on this slide, diatangzone.com. Of course, we decided to check this website, and that's what we saw. You can see that it's a website of some online multiplayer game that offers you to download and try this game. And it's a game in which you can battle other players online with tanks and also earn trade, sell, buy these tanks in form of cryptocurrencies, and like also earn real money with it. And I'm actually I'm really huge fan of video games, and like when I saw that there is an option to like download this beta version of the game, I really wanted to press it and play. But actually, this was not the goal for the attackers, because as soon as the victim opened this website, there was like deep inside there was a hidden script that would download some additional script from the servers of the attackers and execute it. And this script, it was an exploit for the Google Chrome web browser. It exploited unknown vulnerabilities, so it was a 0-day. And with that, attackers were able to infect like any user of Google Chrome web browser as soon as it just visited this website. Like it's all what was needed. And after that, they will just execute the malware and like do whatever they want with the victim's machine. As soon as we realized that it's a 0-day, we sent all the details to Google. And thanks to Google, like they work always really fast. Like in just a matter of 2 days, they fixed all the vulnerabilities and released an update. And today I want to talk about these vulnerabilities. All of them were present in Google Chrome's JavaScript engine that is called V8. Actually, like it's the most popular JavaScript engine at this current moment. Like it's used by Google Chrome, Microsoft Edge, and other web browsers, and it's all in Google's development. And this JavaScript engine has a quite complicated JavaScript compilation pipeline that consists of one interpreter that compiles JavaScript code to bytecode and then executes it, and multiple just-in-time compilers. There is Sparkplug. It's a non-optimizing just-in-time compiler. It produces not an optimized code. Like the code that it produces, it's machine code, but it works just slightly faster than the bytecode executed by the interpreter. And then there is also a highly optimizing just-in-time compiler that is called TurboFun. It produces highly optimized code, but this code generation takes too much time. This code, it takes too much time to be generated. And actually, performance between, but it works very fast. And performance between code generated by the TurboFun and executed by the Ignition and Sparkplug was so big that at some point, Google's engineers decided to create a new just-in-time compiler that they called maglev. It's a fast optimizing compiler. Its single code goal is to produce the fastest code and produce this code as fast as possible. And its relatively new component was added in the end of 2023, and attackers exploited vulnerability in this exact relatively new component. So right now we will take a look at the bytecode, at the machine code, and like what's the best way to dump this bytecode and generate machine code. There are two options. First one, it's possible to compile V8 separately from the Google Chrome, like from the rest of other components that are present there. It's possible to compile it just like a command line utility that also comes with very helpful utilities that could be used from the JavaScript. They allow you to dump layout in memory. Basically, it's what developers of V8 engine use for the development, and also what exploit developers use, because it's a very handy instrument. Another option is just to use like these provided binaries of Chrome, release ones, with special command line arguments that also allow you to dump bytecode and get the addresses of just-in-time compiled code. So here's an example for the bytecode generated by the Ignition interpreter. Well, Ignition, it's quite simple virtual machine. It has quite a lot of instructions, but like all of them are register-based, and there is also some special accumulative register that is used by most of the instructions. But basically, like each opcode, each instruction translates to some specific instruction handler that properly unwraps all the arguments JavaScript variables pass through registers. Also, the type gets recognized. This information will be used for just-in-time compilation. And here you can see the machine code produced by the maglev compiler. You can see that it's a very optimized code. It doesn't actually perform any checks. It just gets the address of the object and sets these properties, these values. This code just stores them somewhere into storage area inside of this object. So it's very optimized code. And here's a trigger of vulnerability that was used by the attackers. I just copy-pasted it from the exploit. So let's take a look at it. At first, you can see that it initializes some array of 2 elements. Then these elements are removed with pop operation. And then it also creates some dictionary. And this array dictionary returned by this calling trigger function. But seemingly, no real work is done with this array and dictionary. And then there is also this call to a function f in a loop. And we also can see the function body. And it's quite simple. It basically has only this one expression, which sets the exported variable of a module to this floating point number. And it checks if exception happened. And by idea, it should always return false or true, right? But code here, it should always return false until, for some reason, it returns true. And we as developers, we know that it's not how usually programs should operate, right? So let's take a look at the bytecode produced for this expression. Basically just these 4 instructions. And all comes down to set named property operation. If we will take a look at the code of this handler, we will see that in this case, this operation should always throw an exception, because this operation, according to the specification, it should not always be allowed, because writing to the module namespace from the JavaScript, it's not allowed operation that should not be performed. But if we will wait until this exact operation will be executed a couple of thousand times, and JavaScript engine V8 will decide to optimize it, and we will see the code produced by the maglev compiler, we will see such machine code. And you can see that it doesn't throw an exception. It actually performs this write. So it just stores a pointer for the JavaScript object for this floating point number somewhere inside of this object for exported module. So this is forbidden operation that should not have happened. And this inconsistency, this forbidden operation that happens, this is actually a vulnerability that was exploited by the attackers. So here you can see also how it was fixed. Developers also added these checks to the maglev compiler to check that the code should not set properties of some forbidden objects like exported model. To understand how it was exploited, we need to understand the layout of objects, how they look in memory. And in V8 engine, all JavaScript objects are represented by a similar structure. So all of them start with a pointer to an object that is called map. And this map, it describes a shape of the object, it tells the engine what this object is and how it should be treated. Most interestingly, there is this integer value at offset +8. It's called instance type. And actually, this integer value is used by the engine to determine what this type of object is. And if attackers can somehow replace this value or make engine to read some other value instead of it, all of this leads to vulnerability of type confusion. So because engine will mistreat the object, it will lead to a trivial memory corruption that could be exploited for code execution. So here you can see JS receiver. It's a very generic type of object that is created for the exported module. And basically, it's the most generic type of JavaScript object that might have some set of properties. And these properties, they're represented by the object of type property array. And if it was not module object, but some other generic object, setting a property will just overwrite this value at property 0, at offset +8. It will just write an integer there or write a pointer of another object there. But because like this operation should have not been happening in the first place. This write set in a property happens using some not initialized index. So it happens that it just overwrites the pointer to the map. And as we already know, this is very bad. So with that, they just write the pointer to the map with a pointer to the controlled object that they create for the floating point number. And the floating point number in JavaScript has such structure that attackers can just use it to provide any integer value for the instance type they want. So it's exactly a type confusion. So with that, like in JavaScript, properties might be represented by the two types of objects. There is property array and also a property dictionary. And the problem with that is that, like it's different objects. They are different in size and have different offsets, located at different offsets in memory. Property dictionary is much larger object comparing to property array. And also it has hash, something that property array doesn't have. And it could be like, it's possible to trigger its generation at runtime, and it might happen that it will write some other field located in some other object located close to original property array. So with that, all what attackers need to do is just to achieve the desired layout in memory. And that's exactly what is happening. You can see the animation. So first, they create this array of 2 elements. They remove elements from there. They need to do that because, first of all, they need to have a desired layout. And also, they need to have the size of this array equal to 0, because if it's equal to 0, then they might trigger the generation of the hash, and it will override this size. It will be like the hash, it's some random value, so it will be, the size will be written with some random value, but it will be still huge enough. And after that, the JavaScript engine will be thinking that it's an array with very large size, and attackers will be able to use it to access the memory of some other objects located close nearby, modify, read them as they wish. And what they do is that they can create some array that of very huge size that will cover all the address space. They might also compile, with the help of maglev, special gadgets that would allow them to read pointers of objects as integers. So they will get this classical get address of primitive. And with that, they will be just able to manipulate the memory of any objects they like. But the end goal for attackers is to get code execution. And everything is not so easy anymore, because right now in V8, there is this new mitigation that is called V8 Sandbox. So in Google Chrome, all the pointers that you can see here, they're just 32-bit addresses, 32-bit values, but actually it's 64-bit process. It happens because Chrome has technology that is called pointer compressions. So all these pointers, they are actual pointers, but like it's not the whole pointer, but only the lower part. Or you can think about it like an offset from some base address. And an actual base address is stored inside of some CPU register. And with that, we have something like looks like some cache, some area with all JavaScript objects, and all of them are linking to each other only using these offsets. And these objects also do not have any like real pointers. And also, like some very important memory regions, such as stack or memory pages of just-in-time compiled code. It's like separate memory regions. And inside this, let's call it V8 Sandbox, there is no like direct references to these regions. And also, as all objects reference to each other, not using real pointers, but using these offsets, attackers do not have primitives to like read and write some memory outside of this area with V8 objects. So this is the general idea for this mitigation technique. And to bypass it, attackers need additional vulnerabilities. And attackers used a very cool vulnerability, in my opinion. They exploited another interpreter that exists in V8 engine, And this interpreter, it exists only to allow users to execute regular expressions. So each time you write a regular expression from the JavaScript and execute it in Chrome web browser, there is a special virtual machine, gets this regular expression, compiles it into bytecode for this virtual machine, and executes it with a special dedicated virtual machine. It's quite simple. There is not so much instructions. It's also a register-based virtual machine. There is some specific amount of registers. Basically, it's just some array in memory, and all the instructions, like they just get the desired index of the register from the bytecode from the body of the instruction, and then code accesses like the desired register using this index. And the vulnerability was that none of the instructions actually checked if this requested index of the register fits into the boundaries of this array for the registers. So with that, attackers were able to craft their own bytecode and read and write memory outside of this registers array. And also, in this virtual machine, there is this instruction succeed. It exists, it has only one purpose. Just to glue this virtual machine with just regular JavaScript execution environment. It just copies some requested amount of registers from this virtual machine back to JavaScript. So basically, it's just a memcopy operation, and it writes the data using some variable, a pointer, and also it copies some amount of code words using also some variable. And unfortunately, like these two variables, the output registers pointer and output registers count, they located in memory right after this registers array, and attackers were able to read them, modify them, and just use this succeed instruction to just write any data they want at any location they want. And this way, they just read the stack, they found the location of the just-in-time compiled code, and just memcopied the actual code there, and it was executed. Shellcode, it was a validator. If you've seen our presentation about operation triangulation from the 2 years ago at CCC, like this concept, it will be familiar for you. Very advanced attackers, they do not provide like the whole stage, like the whole exploit chain they have. Like they do not ship all the exploits they have. They prefer to perform some validations to make sure that it's not the analyst, to make sure that like it's the real victim. And it also was in this case, so like this shellcode only validated like all the information about the infected machines they could get. All this information was sent to the server, and the server decided if they should provide the next step of attack. In this observed case, another problem was that Lazarus group, usually they, while they had like this website distributed in 0-day, the actual 0 days were enabled in some short periods of time. So they had this website, they had this bait, but when it comes to the exploits, they will just turn them on, do some publications to attract people, and then instantly also, like when they get enough of infections, they will disable it, process the victims, and then like repeat. Also to make sure that if this campaign gets discovered by the anti-malware researchers, like to make sure that they will not burn the exploits. But we were lucky; we were able to capture the remote code execution exploit. But when it came to the additional exploit, in this case, it should have been elevation of privilege exploit, most likely some Windows vulnerability, most likely kernel one, to escape App Container Sandbox. So in this case, we decided to not wait for additional waves of attacks. Throughout the years, like we've discovered tons and tons of 0 days that were used by different threat actors in different campaigns, like all the CVEs that you can see on this slide. Like all of these were like really actively exploited 0 days used by the different national state actors, by the cyber criminals in attacks on real users. So we have like these capabilities and knowledge to find, discover, capture 0 days and get them fixed. But in this specific case, we had to wait for additional waves. And we've decided that in this case, it's a bad thing to do because while we're waiting for the new infections, they might actually infect more people. So, and also like fixing the remote code execution part, and I think most likely it was the most important and interesting thing in this attack. Like only fixing like the first exploit would just render all the campaigns no longer usable because they will have to develop new remote code execution exploit, which is very problematic. And if they will do it in the future, we'll still will have the chance this time to get like the full chain. So yeah, that's why we decided to not wait. All vulnerabilities were fixed as soon as we discovered them. So that's all what I wanted to tell you about the vulnerability and exploit. But that's not all interesting that I can tell you about this campaign. It always impresses us how much effort attackers, Lazarus group, put into like the social engineering aspect of the campaigns. And in this case, they've spent months posting different stuff from multiple accounts on Twitter, X, just to promote the malicious site that was distributing 0 days, just to make sure that more people interested in cryptocurrencies will just visit this site and will be infected. And it also worth noting that they've been trying to get in contact with different crypto-influential people who are famous in cryptocurrency world, also to make sure that to make them to promote like this malicious website, to get more people infected, and also most likely to infect these crypto-influential people as well, because most likely they have a lot of cryptocurrencies. And all this malicious social engineering activity was not limited to Twitter or X. They also had malicious accounts in LinkedIn. You can see it's like premium accounts to make sure that they like can see whoever visits their web pages. And they even had a special dedicated groups in Telegram and Discord. So like it was possible to write them, you can communicate with them. And the longer we talk about this campaign, like the more crazy it goes. Because you remember it was possible to download this game. Actually, this is what this website promised. So is it the first game from an actual APT group that we can actually play? How awesome it will be. Of course, I just couldn't wait. I downloaded this archive. And it was archive of quite decent size. And inside I found structure that is very typical for the game written in Unity engine. And there is also, you can see like the project of the name. So it looks like the Lazarus actually compiled this name. The project name matches the name of the domain. So I had a deeper look. And I found that actually like there is a folder with something that looks like a real resources of the game written in Unity engine. And also, I found debug artifacts for this project. And it also shows that like the name of the malicious domain is present in this compilation of artifacts. So it's clear that developers actually compiled whatever it is. So at this moment, of course, I decided just to launch it. So let's check. So yeah, the logo matches the domain name. And of course, I've tried to log in. You know, it's a multiplayer game. And usually how it is with online games, to play it, you need to put your credentials. And there is a button for login, there is a button to create account, there is a button in case you forgot your password, but none of them worked. And I checked the website, and there is also like the page to create your account was also missing. So is it all that this game has to offer? And of course it will be most likely, because why would attackers need to develop like the actual game that you can play if like all what they needed is just to get people visit the website, right? But still, like this thing, I was thinking about it more, and I decided to unpack all the resources. And inside I found that like there are real resources of the game, like textures for the tanks, HUD elements, 3D animations, and so on. So like it's a real game. Wow. I started to reverse engineer the code, and I found code, like for this calculation of the damage for the tanks, code for spamming the tanks. So like everything looks like a real game. So like I got really inspiring. I even found that there is a code for communication with the game server, and it was clear that it's just not working. Like the server is offline. Actually, like this website that they had to distribute their days, they also had to run a game server on this exact website, but they were not doing it. So of course I decided to create my own game server because I really want to play it. And how hard it could be. So I analyzed this protocol, like it uses socket.io, commands are obfuscated, the payloads, the actual payloads, they are encrypted with IAS, also encoded with basic, like you get the idea, like how much effort put into that, right? Of course, I like implemented all of this in small Python script. So let's check how it looks. So yeah, I put my name, my password, log in into my own server. I can select like the very powerful tank that I also cheated for myself. I can select the level, and yeah, this is a game. Like it's actually possible to play it. Yeah, I mean, it's kind of fun. Like you can play it, enjoy it, but yeah, there is some technical problems. Like these blue spots. It's actually where the water should be. Yeah, so like, yeah, like it looked like they really put a lot of effort, but still, they had some problems. But wow, like it's the first time when I actually see that APT also shipped an actual game that you can play. And how awesome it will be if all the malware authors, all the APT actors also developed the video games and provided them these games with malware. Like this would make our lives of malware reverse engineers so much more fun. But like Lazarus, what they do the best is just steal stuff. And turns out in this case, like the source code of this game was also stolen. And it's crazy how much effort they put into like redrawing all the logotypes, replacing them, removing all the mentions of the original project. I don't know. I think they were expecting that someone will unpack all the resources and will take a look at them. So yeah. Yeah, I was able to find the original project. It turns out the Detang zone is like completely made up thing made by the Lazarus. Our original project is called Defeat Tankland. I found the Twitter account. They have many thousands of followers. And I also was able to find the Telegram chat with more than 1,000 people in it, like real investors who like really interested in this project, investing in their own money into it, and so on. And when I found this Telegram chat, I was able to build like the actual timeline for this attack. So here you can see this timeline. So in the January of 2023, the original developers announced their projects, and almost 1 year later, attackers announced their malicious campaign and started to attract more people and started to infect more people. And only after 2 weeks after this evil doppelganger appeared, the money from the hardware cold wallets of the developers were stolen. So there was this time gap in which developers had a chance to discover that actually their source code is stolen and like it's possible to download compiled game. Actually, the developers not released this game at the time. But unfortunately, like they didn't notice it, and yeah, the money was stolen. Yeah, and unfortunately, it looks like they still were not able to recover after it. So right now comes time for the conclusion for my talk, and what I want to say is that even Google admits that historically, half of the all vulnerabilities found in V8 engine affected its compilers. And you can see that compilers are constantly being rewritten, which leads to new vulnerabilities. Just recently, developers announced a very huge changes to turbofan, which of course should lead to new vulnerabilities that will be exploited by the attackers most likely, or maybe even already exploited right now. And what we can do about it, like especially security researchers, like I might remind you that security researchers are also a very interesting target for the Lazarus. They performed a couple of waves of attacks that were targeted specific at security researchers. Like what we can do to protect at least ourselves. Unfortunately, not that much because, like, it's not possible to use modern internet, web browsers without JavaScript at all. Like the web is just unusable. But there is a solution, and it's a web browser without just-in-time compilation. So there is Microsoft Edge, and it has this security mitigation. The developers call it super duper secure mode. And basically, all what it does is just disables just-in-time compilation. So it's basically just what JavaScript developers recommend you to do. Now, it's very easy to enable, you just need to go to the option, enable strict option. It also could be enabled with a group policy for the whole organization. And I have been using this feature for a couple of years. I haven't noticed any problems. And actually, like at this exact moment, I'm thinking that just-in-time compilation exists in web browsers just to make sure that web browser developers have work and also exploit developers have work. But actually, don't get me wrong, like still, if you enable this feature, like there will still be vulnerabilities, it still will be possible to exploit them, but it greatly reduces attack surface. So if you're interested in securing yourself, I really recommend you to do that. And also, like the most important thing that I wanted to tell you with my presentation is please don't underestimate Lazarus Group. You've seen that they're masters of social engineering attacks. I think I've demonstrated that. And they have a very broad range of targets that include security researchers as well. They commonly use 0 days, and protecting from 0 days, it's very, very hard. And just in recent years, they stole billions of US dollars from the crypto industry. This is information from FBI. But the most important thing that I've discovered, I think, is that Lazarus Group don't develop video games yet. So thank you very much. It was a great pleasure to present you this research, and I will be really happy to answer all your questions.
Great. Thank you very much. That was very interesting. Any questions? Yes?
So first question, why did you think they didn't backdoor the initial game, like the download, because that would blow up the campaign much too early, or?
Sorry, please you could repeat the question.
So the game download, they could just backdoor this, right? But that will blow up the campaign very early, or what do you think why they didn't?
If I understood the question correctly, you're saying why they didn't just backdoor this game?
Yeah.
Why they had to use relay? Okay. Very good question, which puzzles me a lot. But, like, I checked this game and it looked like it didn't have any malicious code. So like it just was a clean game. Like I think maybe it was just to add more credibility to the campaign, like to make sure that any visitors who visit the website and get infected, that they do not get like some thinking that maybe like something fishy is going on, like this game, like it's not possible to download it, but like it was possible to download it, yeah. So I think it was just to add more credibility, but they also decided to not infect this game because like if they put an actual malware into it and it will be detected by the antivirus companies, it will just also destroy like the whole idea behind this campaign. So I think they had like really huge goals for this campaign. Like they put months of work into like building all this again, legend, promoting on Twitter. Also put a lot of like money and resources into 0 days. Yeah. So I think they had like really huge plans for this campaign.
Okay, thank you. One speculation could be that's something I always wonder. Maybe, or I would do that maybe, like manipulate the server so you could like trigger buffer overflow in the game at some point, the moment you like. But
yeah, what you're saying actually, like what you're saying is that they might have hide malicious code inside the game using something that looks like vulnerability. Is it correct?
no malicious code, like just normal functionality, but the server triggers a buffer overflow or could trigger a buffer overflow. So the game is fully legitimate, but if the server misbehaves, it could exploit its own game.
Yeah, I understood the question. Basically, it's like the same, you know, like with malware, how it happens, you know, like usually in most of the cases, the malware commonly doesn't have any malicious functionality. It might be just some loader, you know, like stage loader, HTTP loader, that will just make some requests, download an actual malicious payload, shell code, and executes it. Like it's a very common technique that is used by the attackers, very common, but doesn't really help because common security, like modern security solutions analyze the behavior. So in case if like it's some very rare and common binary that actually starts to perform something malicious, it doesn't matter like did an actual malicious payload came from the server or like from some other place, like it will still be triggered. So yeah.
Okay, thank you.
All right, any more questions? Yes?
Great talk. So one of the questions was like, so it exploited old days in browsers, right? But after that, did you analyze like it was like Chrome process doing something funky to steal the crypto tokens or something like that? And if yes, then why wasn't that action detected in an enterprise environments?
Now, could you please repeat the second part of the question?
So like it could have been detected easily, like your Chrome browser is now behaving funkily, like it shouldn't be doing this, right?
Yes.
And of course the ODA is not detected, but the actions after that could have been easily, and my question is like...
Yeah, so the question is that,
Or their TTPs were something novel.
Yeah, so yeah, of course there is TTPs. Like the biggest one, of course, is the usage of manuscript. Like Lazarus, like there are some actors who like prefer to do the operations like in the shadows. So they really care that no one ever sees the malware and so on. With Lazarus, like they just use the manuscript, the variants of manuscript, other malware that is based on manuscript. So like it's the hugest TTPs. There are also some additional TTPs. We published them in a report dedicated to this campaign. So if you're interested, I recommend you to check it out. Yeah, there is, of course, like, yeah, how we discovered it. Like we also have some smart things to detect exploitation of the browsers. Like that's what we do to find 0 days. Yeah.
Thank you.
All right. Is there another question? Maybe I have a short one. You showed that in Edge you can disable just-in-time compilation. Do you know if that's also possible in other V8-based browsers like Chromium or Google Chrome itself?
As far as I know, it's not possible to enable this feature in Google Chrome. Like, for me, it looks like it's like this feature only available in Microsoft Edge at the moment. So yeah, it's a downside for many people, I believe, but it's great for the security, I guess.
Thank you. All right. If there are no more questions, also feel free to contact the speaker afterwards if you have more questions. But for now, give her another round of applause for the speaker.
Thank you.